I'm going to look at some reactions that amines can undergo. So we're looking at some different ways to prepare amines. And so this will be some of the same reactions, because reactions that amines can undergo can also be a way to make an amine. So one reaction that we've already looked at is alkylations and acylations. And so if you had some kind of an alkyl halide and you react that with amine, you get the SN2 reaction. Which again, you could get multi-alkylations from that, because your nitrogen in here is nucleophilic, more nucleophilic now, so it can react with more of your ethyl bromide in this case. So acylations, we looked at that one as well. Looked at if you had an acid chloride, again your nitrogen can replace that chlorine to make an amide in this case. Now we talked about the multi-alkylations that you can see. There's actually a reaction that takes advantage of this multi-alkylation, and that's what's known as a Hoffman elimination. The first step is the conversion of the amine into a good leaving group, and you do that by reacting it with an excess of your alkyl halide to get it to react multiple times. So I have my amine, and so I'll react that with an excess. So this just excess stands for excess. So use an excess of your methyl iodide. So it'll add once, makes it more nucleophilic adding. You have an excess, so it's just going to keep adding, and it actually keeps adding till you have a quaternary nitrogen atom there. And so it reacts 3 different times. So I still have my iodine here as a counterion. And so now that's a really good leaving group. So you treat that with the base. You treat that with the base, and the base abstracts hydrogen, forms your double bond, kicks off your leaving group. So you end up with your alkenes. That's why it's known as the Hoffman elimination, because you're forming your double bond. The least substitute alkene is formed as a major product in the Hoffman elimination due to the large size of the leaving group. The attacking base must subtract a hydrogen from the most sterically accessible position. So if I look at this reaction, so here Now this one I didn't have any other choice. There's only one place for it to abstract that proton from. Here there's a choice. There's two adjacent positions here. So since this is so bulky, this one is harder to get to, so it's less sterically accessible. So due to the large size of the leaving group, the attacking base must abstract the hydrogen from the most sterically accessible position. And so my base will take the proton off of the one that's easiest to get to, forms your double bond, kicks off your leaving group. And so you end up with trimethylamine as your byproduct. Okay, so that's one position. Now if it attached here, which in most elimination reactions, this is a product that we would expect because it's the more substitute alkene. So this one's di-substitute alkene, this one's monosubstitute alkene. So that's what's unique about the Hoffman elimination, is because you make the sterically hindered leaving group, it takes off the most sterically accessible proton, and so you end up with your least substituted alkene as your major product. So if you did this reaction in the lab, you can kind of see just how much more that least substituted product is favored. So let's go ahead and look at a problem. Let's look at A. So this, or 24-14A. So what products would you expect from Hoffman elimination of the following amines if more than one product is formed? Indicate which is major. So if I'm looking at this reaction, so here's my nitrogen. So the first thing that's going to happen is that I'll transform that into a good leaving group. Now here I have two adjacent positions. Okay, here they're probably going to be almost equally likely because this one's maybe a little bit longer on that side, and so this one may be slightly more sterically accessible, but they're going to be close to the same. So if I take off this one, this would be a CH, and then I have 1, 2, 3, 4. There I have 3 octane. If I took off this one, then I'd have 1, 2, 3, 4 octane. Okay. So you can see 3 octane and 4 octane are formed. Okay. And there's not one that's really more favored over the other one because they're about equally sterically accessible. What about this one? Again, if I drew out what my leaving group was, so if let's draw out what that would look like. So I'm saying an excess of my methyl iodide. And then I react that with a base and heat that up. Now this is my leaving group after it adds the 3 methyl groups. There's 2 adjacent positions, but it doesn't matter because I'm going to get cyclohexane in both cases. So in that example, I only get the 1 product. So here's my leaving group, takes off an adjacent proton, forms my double bond, kicks off my leaving group. Look at electrophilic aromatic substitution. So we covered these reactions at the very start of the semester when I looked at aromaticity. So amino groups are orthopara-directing activators. One problem is multiple alkylation since the amino group is highly activating. Another problem is that Friedel-Crafts reactions will not work because amine reacts with the Lewis acid catalyst. To accomplish monosubstitution reactions in the form of Friedel-Crafts reaction, it is best to use amide in the primary reaction and then convert the amide into an amine. So if you start out with amine, I cannot do a Friedel-Crafts reaction on that because a Friedel-Crafts reaction requires a Lewis acid catalyst and the amine will react with that. And so what I can do though is first convert your amine to an amide. So I can react that with an acid chloride to make my amide. So now that's not going to be as reactive, so I'd get monosubstitution reactions, and I'd also be able to do a Friedel-Crafts. So let's go ahead and do a reaction. Let's do bromine. So bromine is adds a Br when you do bromine with your iron 3 bromide. And so this would still be orthopara-director. You'd mainly probably have the para product just due to steric hindrance. And then after you do your reaction then, you can hydrolyze it back to your amine. So hydrolysis just attaches to your carbonyl, kicks it off as your NH2 as a leaving group, so you end up with your amine back. Like I said, you could do a Friedel-Crafts here too and add a methyl group in it and still work because this is no longer an amine. It's a amide, so it would not react with your Lewis acid catalyst and the reaction would take place. Let's go ahead and look at a new reaction known as the Sandmeyer reaction. primary arylamines react with nitrous acid. You can write it out as HNO2 or HONO. HONO is a little more fun because it's like kind of fun to say HONO. But HNO2, so nitrous acid, yields stable arene diazonium salts, which are very electrophilic. So you have your amine. You react that with your nitrous acid. So what your arene diazonium salt looks like would be this. Okay. So those things are very electrophilic, and so you can react them so you lose nitrogen as a byproduct here, but you can react with the various things. You can replace that N2 with chlorine. You can replace it with the bromine. You can replace it with the iodine. Just whatever your nucleophile is, in this case KCN, so your nitrile is your nucleophile is CN minus, and so that would replace it. You can replace it with an OH group. That's a little more complicated. Use a mixture of the copper 1 oxide, copper 1 nitrate, and water. So that's how you can make a phenol. And then you also you could also react it with H3PO2, and it just adds a hydrogen in place of your diazonium or your N2. So you end up with your benzene back. So let's go ahead and look at a problem. Says, how would you prepare meta-hydroxyacetophenone from benzene using a diazonium replacement reaction in your scheme? So the only diazonium replacement reaction was, the only thing that we looked at in all of those previous reactions was that OH group. So I'll do that one. So I can use that in my scheme to make that OH group. Okay, so there's my diazonium salt. Now I know I can use that to make my OH group. Now how could I get those different things on there? Well, I can use my nitrous acid on an amine. Okay. And now we've got the amine now, but how can I add an NH2 to it? Now this is a meta director, so I could add something there, but what could I add? Well, if that was a nitro group, I could change my nitro group into my amine, my NH2. And that's the reaction we covered. The tin chloride with the acetic tin chloride is the reaction we covered there. And we went over the aromaticity chapter at the start of the semester. So now these are both meta directors, so I could just add one or the other. So I could add my nitro group to my acetophenone. And then I could also, now it says from benzene, so I could do a Friedel-Crafts acylation there. To get all the way back to benzene. These diazonium salts can also be used to couple with a coupling reaction with activated aromatic rings, so something with a lone pair of electrons that activates the ring. You need something that's strongly activating to yield brightly colored azo compounds. Azo coupled products are widely used as dyes. So I don't know if you've ever heard of azo dyes before. So in this reaction, you have your diazonium salt, plus an activated aromatic ring. So this is something with one pair of electrons, so something with like an oxygen or nitrogen on it. So what it yields, so this ortho-pair director, it's going to yield, it's going to all attach to it, so it's actually going to attach to the pair position. So that compound's highly conjugated. So remember, highly conjugated compounds have color to them. And so that's why these are usually very colorful and are used as dyes. The last part here deals with heterocycles, and I talked about heterocycles before. So a heterocycle is a cyclic compound that contains atoms of two or more elements in its ring, usually carbon along with nitrogen, oxygen, or sulfur. Heterocyclic amines are particularly common and many have important biological properties. And here's some examples of some heterocycle amines. And so you can sell some pharmaceuticals, heme, oxygen carrier in blood is a heterocycle. Here's a coenzyme that's a heterocycle. So, but that wraps up the chapter on amines, and so the next videos I'll do will be reviewing for your exam. Bye.